necessary for the performance of work. There must be an applied force F. There must be a displacement X. The force must be a component along the displacement. The equation for work is force component times displacement. The work units are joules. Work can also be calculated at an angle with the equation of F cosine theta times X. Lastly, the law of conservation of energy states that energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes.
Okay, potential energy is energy that is stored. An example is an object on a shelf or a slingshot. Okay, the equation for potential energy is mass times gravity times height. And kinetic energy is if we do work on an object, we can change the energy of motion. The equation for kinetic energy is half of mass times velocity squared. It's mass is kilograms, gravity is 10 meters times seconds, and then the height is meters. So, and the equation for kinetic energy is Ke equals half of the mass times velocity squared. So, yeah. Doing a demonstration of the conservation of energy, which means that energy cannot be destroyed nor created, it can only be transferred. So today I'll be using a pendulum, which means that at the top of its swing, it'll have 100% potential energy. At the bottom of its swing, it will transfer into kinetic energy, and at the end of the swing, it'll have its maximum potential energy. And you'll notice that it will not hit my face. So. We will be applying our demonstration to this problem. So first thing is we have to plug it into the problem. So this ball weighs about 6 ounces, which converts into 0.17 kilograms. And we're going to put it at a height of 6 feet, which turns into 1.82 meters. So we're going to see how the potential energy and the kinetic energy transfer throughout the whole motion. So
Energy of a 0.17 kilogram ball traveling at 10 meters per second at a height of 1.8 meters is equivalent to 3.06 joules. Potential energy is transferred into kinetic energy, therefore potential energy equals kinetic energy. The 3.06 joules of potential energy is equal to half of 0.17 kilograms times velocity squared. After all the calculations, we got 6 meters per second.
Okay. We'll show how potential energy transfers into kinetic energy. So at the top of the slide, the ball will have its maximum potential energy and its minimum kinetic energy. And as the ball goes down the slide, the potential energy will be at its minimum and the kinetic energy will be at its maximum. So, here's our demonstration.
Highest potential energy at the top of those swings.
3.
The ball's potential energy was transferred throughout the whole swing and transferred into kinetic energy. At the bottom of the swing is the highest kinetic energy.
Hi, my name is Montrose. I'm going to show you how potential energy transforms into kinetic energy with the jump loop. As seen shown here, as demonstrated, when I have the ball in my hands extended outwards, I have potential energy.
Yeah. Right now, as he is sitting on that swing, he has full potential energy. And is just transferred into kinetic energy. And back to potential. And back. And back.